Hi everyone. In this video, we're going to discuss a few challenges related to machine learning algorithms. The first and foremost challenge for any machine learning algorithm is its ability to generalize beyond the training set. So what we have seen is that we use a set of training data in order to learn patterns for the model of interest based on this training data. And these patterns can actually be used in order to learn the structure of the model. However, we do not know how much the patterns that have been learned using a specific model and a specific training set can be generalized on a set of unseen data. And the challenge for generalization is one of the biggest challenges in machine learning. Ways to avoid, ways to make this generalization better for a machine learning system is first of all to excessively test it over different sets of testing data and different sets of validation data. And throughout the semester, we are going to see various techniques to do that, including leaving a test set and a development set out, conducted cross-validation or nested cross-validation. Another challenge that is very difficult for machine learning algorithms and sometimes might be related to the challenge of generalization is the challenge of overfitting. So this refers to the risk of using a highly flexible or highly complicated model without having enough data. So on the left side of this figure, we can see a set of training data, which is depicted with blue dots. And then with solid black line, we can see the polynomial that has been used in order to fit this data. This case has used a 14-order degree polynomial, which we see that kind of fits this data in a decent way. We see now that if we use for the same data a 20th order degree polynomial, then the overall final model is a model that it is completely non-appropriate for the structure of our data, which is essentially the general shape of the structure of these blue points. So ways to avoid overfitting include regularization, which refers to constraining our model not to become overly complicated. And of course, we can use validation and cross-validation in order to ensure and in order to better understand whether our model has overfit or not. The third challenge that is inherent in many machine learning algorithms is the curse of dimensionality. Nowadays that we have way more data, we also tend to have highly dimensional feature spaces. The problem with that is that the more dimensions we have, the harder it is to systematically search these feature spaces for appropriate models in our search space, and it's harder to approximate them. So if we have high dimensional feature spaces, usually we need also a large number of samples in order to adequately approximate. A good thing overall is that if we have a high dimensional feature space, it doesn't mean that all parts of the feature space are uniformly equipped with data. So it might be enough just to simply approximate the parts of the space that are more densely equipped with data. So this is what we call the blessing of non-uniformity. Feature engineering is another challenge that is also highly relevant to the curse of dimensionality. Usually, the best thing would be if we have a task and we can engineer, or at least we can learn a low dimensional feature space that is highly representative of the task that we have. In the previous video, we had seen the example of flower classification, in which we had understood that attributes related to the sepal length and width of the flower, as well as to the petal width and the length, are indicative of the type of the flower. If we have such types of intuitions, usually we are far more likely to reach good feature spaces without having the cost of high dimensionality, which increases our computational cost, as well as it also increases the requirement for large number of samples. In terms of feature engineering, over the last years, we have seen that the feature learning via deep learning representations has been one of the most common ways to go about feature engineering. And there's definitely a lot of value in actually learning features from the data rather than prescribing features and actually constraining our data spaces with specific features. However, feature learning approaches also need a lot of data in order to be accurate. Finally, we have to keep in mind here that there is no free lunch theorem. As it was mentioned many years ago, all models are wrong, but some models are more useful than others. There are some general assumptions that can actually work pretty well. For example, similarities between samples, as well as independence and smoothness assumptions. And it's also very important to keep in mind that machine learning is not magic. There's no model that works best for everything. And there is no algorithm that actually is the best. We have to see what works for our data. We have to obtain intuitions from our data, perform exploratory analysis, understand what works best, and then, of course, thoroughly design and evaluate the machine learning algorithm.